means until somebody, something, some external agent moves it. Some work is done. For example, this book lying here shall lie here for an infinite period of time. It will only go up if I move it. If I move it, it means I'm putting some work into that. So if this block goes up, means the height changes. We said something changes inside that was later known as energy or work. We said that if the state parameters inside the box, they change from E1 to E2, we can say that the mass can be raised. Okay. Now you can know that we already know this. You know this is the formula for the potential energy, mgh. If I move it and if I want to know how much work I have put into this book, I just need to weigh the book, calculate the mass, and then measure this height. I can know that. The difference between this text and the regular thermodynamics text is that when we are defining heat, energy, and work, we will not use, because they look like similar terms. If you just based on your GCSE and A-level knowledge, you will not be able to understand the difference between energy, heat, and work. You will all the time, they are all energies. But in here, when we are defining energy, we are not using the term heat, we are not using the term work. When we will define work, we will not use the term energy. And when we will define heat, we will not use the term energy or the work. So, this block can only be raised if some parameters changes inside. So, if the state parameters goes from E1 to E2, so this is the effect. And we say this is adiabatic. Adiabatic means it is not interacting. The only interaction this system is having is through this frictionless mechanical pulley. It means there is no entropy, no friction. So a very good example is quoted in the Giftopoulos book, in which he has provided a pedal like this, and a compressed gas is over here. And now, if the compressed gas expands, it will move the pedal like this. So if the pedal moves, the mass will be raised. So this is first law of thermodynamics. So you need to understand this. For if Professor Alexander asks you to define the first law of thermodynamics, why PMM1 is impossible, all these things are related to this diagram. What PMM1 says, that if you are moving in a cyclic process, you can still generate some work. But this relation, the first law of thermodynamics says, if you end at the same height, means cyclic process means after some time you restore yourself back to the original condition. If H1 and H2, they are the same, there will be no energy change. Or we can say, if the body is operating in a cyclic process, E1 is equal to E2, it means this side is 0. Ultimately, H1 is equal to H2, which means that you cannot raise this mass if you are operating in a cyclic process. It means that PMM1 is impossible. Okay, so I've already done the interaction. Then comes the adiabatic availability. This is again very important term, and I can tell you, I can disclose a question which is going to come in the exam, and you will see this question has been coming up in the exam all over the years, that if you have a block, the temperature is mentioned, and he will ask what is the adiabatic availability of this block in its initial condition. 2 marks. 0 is the answer. The reason, if it is not interacting, there is nothing available. So you just say 0 for that. Okay, so then comes the temperature. What is temperature? You have never ever heard this definition of temperature before. You used to say the degree of hotness or coldness or measure of energy or something like that. But in real sense, the temperature is actually the gradient of the energy entropy diagram. If you have got the entropy on your x-axis, energy on your y-axis, and this line, now what this line is, I'll come to this. On this line, if you want to measure the temperature at any point, you need to get a gradient. Just draw a tangent. Because if it is a curve, the gradient is not constant. Gradient is changing at every point. So at any point, if you want to know the temperature of the body, just draw a tangent and then measure the gradient of V is delta dE over ds is equal to V. This is, in simplified terms, the definition of temperature. Now what this line is, again, an important thing you need to know, this is the line of equilibrium. What is equilibrium? Equilibrium is a position which should be avoided all the time throughout your life, whatever you are doing. Because once you are in equilibrium, you are dead. You lose all your potential. You see, if you are here, which is non-equilibrium, you should be always in non-equilibrium. Now you are in non-equilibrium because you are looking for a degree to get your career start. Once you get your degree and you say, okay, that's okay, this is my life, I've done it, it means that you will end up as a junior engineer, you will get retired as a junior engineer. You will never ever raise yourself to CEO, Chief Executive Officer of any company. So it means that what you are doing, once you do your degree, you set another level. Then your master, maybe PhD, if you are not going to that route, going to an industry, you are always looking for a higher position. It means that you are keeping yourself in a non-equilibrium position just to keep your potential. Similarly, the thermodynamic system, this is a non-equilibrium region. This is equilibrium line, and these are non-allowable states. Non-allowable states mean that if the ambient temperature is 25 degrees by yourself, without any effort, you cannot go to 24 degrees. Like refrigerator, if you are not supplying the electricity to a refrigerator, your vegetables and meats, that's going to be wasted. Reason? It's not being cooled. Why? Because you are not doing work. Automatically, refrigerator cannot run. If you want to go at temperature beyond this equilibrium line, you need to put work, the way we are doing in the refrigerator. So remember, if this is a system, not reservoir. Reservoir is also a system, but it has got some properties. Because, for example, the temperature of the reservoir does not change. If the temperature of the reservoir does not change, it means that this line is going to be straight for the reservoir. Straight line on energy entropy axis for reservoir and a curve for any system which is not reservoir. These two diagrams are very important because Professor Alexander will keep saying, reflect your result onto energy and entropy, the initial bit and the final bit. If it is a system, you can say on its own. System on its own can lie anywhere on the line. Similarly, the reservoir is here. Now, if you are in a non-equilibrium position, you can do two things. You can do work and you can lose your potential by doing nothing. If you lose all your potential, it means that you need to move on the energy axis, and we know that to do work, you should have some energy difference. You should move on this axis. If you are going from here to there, it means that you have not moved on energy axis, so no work possible. All energy gone wasted. This energy gone wasted is actually the entropy. Okay? We can do another thing, that you can interact with this. Come straight down. If you come straight down, it means that this is the most efficient way of doing a work. So we will say W max. You will get W max when, I'm not driving all those relations because I don't have time. So I'm just revising things that you need to learn, you to remember all the time when you are solving these issues. W max will be possible when DSIRR is 0. If no entropy is generated, W max is what you get. So what is the relation between W max and W actual? You will see the derivation. W actual or W output is W max minus temperature of the reservoir times DSIRR. This is the relation. Yeah. So work all clear. Next comes the real stuff, and it is the steps that have always been emphasizing you to learn. Put them into your minds, if not hearts. Number 1, draw a block diagram. Number 2, write down the energy balance. Number 3, write down the entropy balance. Number 4, see what is required and then do the manipulation. For example, when you are doing something, you write, this is a system A, this is a reservoir R, and you are actually getting some work output. The first step is draw a block diagram with all arrows out. I've done that. Then dE of A, ds of A, dE of R, ds of R. Okay? Then write down the energy balance. Written dE of A plus dE of R plus W is equal to 0. Write down the energy entropy balance. ds of A plus ds of R is equal to dsIRR, which should be greater than or equal to 0. Okay. Now the question is, if you are looking for work, in most of the cases you will be given a constitutive relation for dEA and dSA. If I remember right, you were given most of the time MC T2 minus T1. This was your dE of A for that system, and your ds of A used to be MC ln T2 over T1. You can correct me if I'm wrong. So dEA ds of A. So it means that to get the work, you have minus dE of A minus dE of R. So for this, we have got this relation, but we are troubled by DER. Now, you will be most of the time, like the initial quarter, first quarter of the book, what you will be doing, you will be using your entropy balance to get a relation for DER. And what you do, you use the definition of the temperature of the reservoir, and we know that for reservoir dE over R over ds of R equals to TR, which means that ds of R is equal to dE of R over TR. Now, if you plug in this relation over here, it will become ds of A plus dER over TR equals to dsIRR. Now from here, you can get a relation for DER and plug it over here, so you can get the work. So all these derivations we have been doing in this class, they have been exclusively done in Professor Alexander's notes as well. So what do I mean to say is, for example, if the process is reversible, Wmax, okay, I've already written, I will write again. Wmax will be there when the process is reversible. Because Professor Alexander in exam, he may not say that dsIRR is 0, but if he says reversible, you should take it as dsIRR is equal to 0. dsIRR is the entropy generation due to irreversibility. And if there is no irreversibility, it means that there is no entropy generated. So, similar, so on and so forth. So you can do these steps, the 3 steps, and then you can manipulate. And then comes the energy conversion devices. We have studied 3 of them. They were heat pump, heat engine, heat pump, and then it was refrigerator. So again, similar kind of block diagram you were drawing, but in this case, there was no regular system. Both were reservoirs. The hot temperature reservoir and the cold temperature reservoir, and then the movement of the energy. the hot temperature reservoir, the cyclic machinery, the cold temperature reservoir, and the work output. You will do the same thing. Draw all errors out, write down the energy balance, write down the entropy balance, and then see which equipment you are dealing with. If you are dealing with a heat engine, in a heat engine, this is the flow of, the direction of flow actually. So the convention is you draw all arrows out. I have drawn, but I know that this DEH is that way, so I will write negative with that. Work it out. So I will follow the very same steps to obtain a relation for Wmax and its efficiency. Similarly, when you do the refrigerator, in case of refrigerator, you are getting the heat or energy from the cold reservoir, so it means that this needs to be reversed, and sending it to a hot reservoir, and you are not extracting work from the refrigerator, rather you are spending your quids to burn electricity in that, so these two arrows will be different. So if the actual direction of energy flow is different from our convention, we will put a negative sign, and we have been explaining this thing to you. So what you need to do is, for these three, you will get Wmax, and you will get efficiency or COP. The derivation for the heat pump and the refrigerator is very much same. The diagram is very much same, but you will find that COP is different. The reason is that they are two different devices. If, like, you can say, okay, if the block diagram is same, if the energy flow is same, even with the same input parameters, you will get different answers for the COP. The reason being that when you write a COP is a relation which will constitute that how your inputs and outputs and the desired outputs are related. In a refrigerator, we are not bothered what is the room temperature in our kitchen. We are interested to keep the refrigerator at minus 10 degrees C, for example. So it means that it is the relation between how to keep it at that level and how much energy you need to supply. This is the job of the refrigerator. The job of the heat pump is to keep the place hot. We are not interested how cold is the outside in winter. So it means that it will be a relation between these two. Is it clear? So this is how you need to look at these things. Okay, then comes the, I already explained the scheme to solve. The scheme is draw a block diagram, write down the energy balance, the entropy balance, do some simple basic algebraic manipulation and get you what looking for. Next is the steam tables, but before that, these gas laws, nothing serious in gas laws, just page 86, equation 36, I think. That's the only equation which is being used for perfect gas. For entropy, you are given the entropy change in three different equations which relate temperature, pressure, volume, and volume temperature. So, depending upon what you are given, you can pick up the suitable equation and use it. And you will keep using this till the last problem in the book. Then comes the steam table, the next bit. In steam tables, what you were doing, now, up to now, we were just dealing with solids. Yeah, or just dealing with fluids. There was no state change from liquid to gas. But if there is a case, which is the mostly in our, in industry, you are having steam turbine, your water, heated, pressurized, sending the turbine. There is a phase change. For that phase change, we have got the steam tables, and a very exhaustive lecture was given on the steam tables, how to look into the steam tables, and then very small and simple problems are designed for that. I think you should be very good on that because we were checking a few courseworks, you seem to be okay. The last bit is the thermal machinery. I was explaining in the last lecture, I will do it again. plotted that it used to be ES, now it is TS. Yeah. So this is our state 1. This is P1. This is P2. These are the different isobars. On these lines, pressure is constant. From 1, you can go to 2, straight up to S. Means constant entropy. You can go to 2. From 3, higher pressure, you can come up to 4S. You can come up to 4. So the lower configuration, this one, is a pump or compressor. And the upper configuration, this one, is for a turbine expander. Okay. If you are good at steam tables and you know this diagram, no question in the turbo machinery section can trouble you. This pressure will be given, this temperature may be given. You can go up, you have got the entropy. Once you are there, then you can determine the temperature at 2S. If you know the temperature at 2S, then you can write down the formula for the efficiency. You can calculate the actual temperature as well. So what is the formula for the efficiency for compressor? Is the smaller one, which is T2S minus T1 divided by T2 minus T1. For turbine, again the smaller one, T3 minus T4 over T3 minus T4S. So you have, I think, if I remember right, there was another relation. It was T2 over T1 equals to
ln
P2 over P1 R power CP. If I'm right, I don't know.
Yes.
You can check it, yeah? So this is, for example, T2S. So now you have got T1, you have got the two pressure, you have got R, you have got CP, you can work out T2S. If T2S is calculated, just put T2S over here, efficiency is known, T1 is known, T2 can be calculated. And the same holds for the turbine as well. That's done. Finished. Okay. Just 35 minutes job. Okay. The next thing was your lab report. Before I say something about how you prepare for the exam,